Good afternoon and welcome to the ESAB Specialty Alloys live event. My name is Clemente Tallarico and with me as the presenter we have Mr. Peter Stones. As well, Mr. Paolo Turchiana, Global Product Manager Strip and Wire, is there also for technical support. I'm pleased to announce here the 11th presentation of ESAB Specialty Alloys, which will happen every third Friday of the month at 14:30 European time via Time Live event. The 11th presentation of the program will be the one starting in a few seconds with the title How to Maximize Productivity in Strip Overlay Welding. We will be very happy to answer your questions at the end of the presentation, which you can type in the Q&A box you will find in the top right of your screen. We intend to present on about 30 minutes and take 10 to 15 minutes more for answering your questions. So with that said, let us start with the show with Peter presenting. Enjoy.
Thank you, Clemente. Good afternoon, everyone. Thank you for joining us. As Clemente said, we're following on from the previous presentation which was an introduction really to strip overlay welding. So this goes one step further, and we want to talk about how to absolutely maximize, get the most out of the process. I would just point out right from the beginning that we're more than happy to receive inquiries, calls, and our details will be on the last slide. Please feel free to email us. More than happy to send out copies of the slides. Just send a little request and we'll be more than happy to do that. So don't worry about being able to take notes. Obviously, we're only going to talk for 30 minutes, so it's not an in-depth review. Just to give you a flavour of the process and really what is achievable. So right at the start, why do we overlay weld? Why do we want to put a deposit on top of something else? So this is not welding, this is not joining together, it's an overlay. So why do we want to do that? Why use strip? Maybe an obvious answer, but why do we use strip? And we'll just go over again briefly what are the differences between these two processes, submerged arc welding and electroslag welding. Now, electroslag welding has been around a long time, but this is electroslag welding specifically for weld overlay. What equipment is required? Dilution. What is dilution? How does it affect the process, and what can you do to compensate for it, basically, and what deposition rate can be achieved? We're talking about maximizing your productivity, so what is the maximum that's available? So what's the purpose of weld overlay? Why does anybody have to overlay? And jumping right down to the bottom of the list, really, it's economy, it's money. So the strength of the component can't be achieved using the resistant alloy, whether it wants to be a chemical resistance, corrosion resistance. The strength's not there, so you need to make the thing out of high strength steel, but then coat it for the areas that are going to be in contact with corrosion, for example. The main reason really is that it's cheaper than homogeneous material. So alloy 625 nickel chrome moly 3 is a very common, very popular weld overlay grade. So 60% nickel in that. So it's a very common grade for use in all kinds of industries, but it's very expensive. So you wouldn't want to make a 20mm thick vessel from nickel chrome moly 3. The weight of it, the price of it would be well, expensive. So the alternative is, again, to make it from cheaper steel, carbon steel, and then coat it. You may need different requirements from the inside and the outside, so you need to coat one or the other, one or both sides, and possibly the material can't be produced in the dimensions that you want it, for example. So we weld overlay. It's a very common process that's been around a long time. Strip weld overlay is a little bit different, and this is the reason why we use strip. So this is the deposition rate per welding process. So right down at the bottom end, TIG welding, manual TIG welding, GTAW. If you're lucky, you'll be able to deposit something like two kilos in an hour. and that's that's good going. That's a lot of arc time. Whereas if you're comparing it with the strips, for submerged arc welding, you're starting at sort of 12 kilos an hour, so that's 6 times more than manual TIG, but up to 30 kilograms an hour is achievable. But then look at this line for electroslag welding of strip. So it's a different process, it's a slightly different process, and the deposition rates are much higher. So this is for 60 millimeters wide strip, so anything up to 50 kilos is achievable and is being done. So just to review really about the two processes, submerged arc welding. If you look at this diagram, then in section it could be wire, and the process is exactly the same. The strip in this case is fed through the welding head into the base material, and then obviously the jaws of the electrodes, potential between the electrodes and the base metal producing an arc. Okay, and the arc is submerged in flux powder. So the whole thing's traveling this way. So like I say, in section it looks like it could be wire, but imagine this could be 30 mil, 90 mil, 150 mil in some cases, but 30 and 60 are the most common widths of strip. So the arc melts the flux, and the arc melts it melts back the strip electrode, and it melts the surface of the base material. So we have a liquid slag covering the arc, and then as the head moves on, the deposition is on the base metal. You can see there's some penetration into the base metal, but then the slag solidifies. It cools down and it solidifies and remains on top of the surface. That's the process. So the process is entirely the same as submerged arc welding of wire. The strip cladding with electroslag welding is slightly different. It's a slightly different process. Electroslag welding's been around a long time for welding things like railway lines, and it's the same process. It's the same physics that's happening, but in this case, it's a development really of the submerged arc welding process for strip. Exactly the same. You need a strip feeder machine going through some jaws. This is a much hotter process. The amount of power needed is a lot more, and I'll explain that later. So usually these are water cooled. The difference here is that you've got the strip being fed towards the base material, and it's fed into a layer of flux, and now this flux is electrically conductive. So the heat is generated by ohmic resistance, so it's like a light bulb. Okay, that's the difference here. So the molten slag, it's not an arc, there is no arc. The molten slag is melting back the strip electrode, and it melts the surface of the base material. So again, I'll stress again, it's an ohmic resistance, and the difference is the flux that I'll explain a little bit later. So we have the solidified slag, again, direction of travel is going this way. So it's covered by first the liquid slag, and then as it cools, you've got solidified slag. So they're both obviously flux processes with solidified slag on the surface. The big difference in electroslag welding is that it's an ohmic resistance. There is no arc. Okay, big difference. One note about flux is that they obviously both use flux with a solidified slag on top, and it's obviously quite important when we're talking about productivity, especially that the flux and strip combination that you choose enables the solidified slag to detach very easily. You can see from the side view as it's cooling down. So we're still liquid over here. As it's cooling down, it's actually lifting of its own volition, really. That makes life very much easier. If you're having to mechanically remove slag, either grinding, chippers, whatever, hammers, then that obviously adds hours onto the production time. So there are fluxes available. There's a very big range of fluxes to choose from, depending on what you're trying to achieve. So the strip is the same for either process, submerged arc or electroslag. The strip is the same. There's not specific strips for submerged arc and specific strips for electroslag welding. The choice of those, the grades that you use are different, and that's dependent upon dilution that I'll explain a little bit later. So essentially the strips are the same. So there's no special chemicals put into electroslag welding strip. With flux is the thing that's different. So the electroslag welding flux is electrically conductive. Okay, so that will carry the current and the resistance heats it up. That's the big difference. You can't do electroslag welding with submerged arc welding flux. And again, I want to show you the deposition rate just for strip. So this is 60 millimeters wide strip. The deposition, this goes up in a nice straight line really, from just under 10 kilograms per hour up to around about 25 for submerged arc. And then for electroslag, it goes up to 50. So these are real empirical results. What I want to bring your attention to is this, the x-axis here. This is the amperage. So this is the amount of power that you need to put in to achieve these deposition rates. And you can see at the bottom end of electroslag welding, it starts at around about 1200 in order for you to achieve the same deposition as submerged arc. But as the line increases, the deposition rate increases, then you need to up the power supply. You need to up the amps. So this is can obviously affect your choice of which method that you're going to use. So again, talk about maximizing productivity. You need a big power supply. Dilution. Again, we talked about dilution last time, but it obviously has an effect on the productivity, the amount that you're able to achieve, and the way that you weld. As with any arc welding process, when the fusion welded together, there is a mixture. You mix the base metal with the filler metal, or in this case, we're talking about strip as an overlay. However, there's still a mixture when it's welded together. This is what we call dilution, and it's obviously an equation of the weight of the parent metal compared to the total weight of the weld. That's the amount of dilution. Okay, and the big difference between the two processes is that with submerged arc welding that uses an arc, typical dilution is 20%, but more often than not, it's 30%. So 30% of the composition of the strip is mixed with the base metal. With electroslag, doing exactly the same thing, welding it onto the surface, just using the different process, then typical dilutions around about 10%, maybe a little bit higher, but around about 10%. So in order to achieve the required composition in the overlay, okay, you're putting an overlay on there to be corrosion resistant. So say you need a 19% chrome on the surface once it's been welded on. If you start with a 19% chrome strip, then it won't be 19% after you've welded it, okay, because of the dilution effect. The way to compensate for that is either put two layers on, and that's not uncommon, to be honest. With submerged arc welding, if you've got a dilution of 30%, you need to add two layers. Now there's obviously problems with that in terms of welding time, cost, and weight, for example. So another way of doing it is to use an over-alloyed filler grade. So if you want to achieve 19% chromium in the overlay, then start with 21, 22, 23, 24, whatever, to compensate for that dilution. Another method of doing it that some companies use is a compensating flux. That means that there is things like chrome, so there are metallic elements in the flux. So it's nothing to do with it being, whether it's electroslag or whether it's submerged arc welding. You can use a compensating flux. So you compensate for the dilution by adding the elements into the flux. Okay. So in terms of the advantages of electroslag, obviously, if you're trying to achieve maximum productivity, then it's electroslag welding. That's the way that you've got to go. Okay, and these are the reasons why. Really, the speed increases. The speed of travel can increase from 120 millimeters per minute for submerged arc welding, up to anything up to 400 millimeters a minute for high-speed electroslag welding. And we mentioned here high-speed fluxes. So it's a different flux if you want to travel at those high speed. Okay, it's a different flux from standard speed electroslag welding, which is still a lot faster than submerged arc. The area coverage increases by 60 to 80%. You're going faster with the same width strip, so obviously you're putting more area down. With electroslag, you get a better bead surface. It's a cleaner weld because of electroslag refining. So you get a cleaner weld and there's less disturbance, so the bead is generally flatter the better. In terms of heat input, then although you're putting in massively more amounts of amps, you're actually increasing the speed, so the heat input calculation stays about the same, and I'll illustrate that in another slide. And because of the lower level of dilution with electroslag welding, then it is possible, a lot more common, to be able to achieve the chemistry that you're looking for in a single layer. And again, I'll illustrate that in a future slide. So what equipment do you require for this? Typical equipment. You obviously need power supply, whichever size of power supply that you need. The cladding head, water cooled if you're using an electroslag. And we're talking about maximising, so we're talking electroslag. This is actually, it mentions magnetic steering, and these are electromagnets that put a magnetism, if you like, into either side of the strip, and you can use that to change the shape of the weld bead. Really, it's not always required. If you were welding strip that was 150 millimeters wide, for example, then yes, you would need to steer the molten weld pool. So yeah, it's a strip cladding head. So obviously the strip feed unit to enable you to feed 30, 60, 90 millimeter wide strip into there. Obviously column and boom, hang it over the through the middle of the vessel, and some kind of rotator manipulator device. Not a surprise. Okay. In terms of absolute best case scenario, the best way for you to achieve the maximum amount of deposit is, as we've seen, electroslag welding. You need to use the electroslag welding process. Select the grade that will enable you to achieve the chemistry that you require in a single layer. Okay, that will make a huge difference. If you want to go fast and to maximize best case scenario, you want to go as fast as you possibly can, then the flux that you use has to be a high speed flux. So you have to talk to a manufacturer that actually manufactures a high speed flux and look at the deposition rate that they're saying that you can achieve. Alongside another phenomena, if you like, of the flux is that it has to be able to detach. You don't want to be climbing in a vessel with a grinder to get rid of the slag. Okay, that's best case scenario. Everything's going in your favor. This is a table that just illustrates the various processes. We're starting off at the left hand side with submerged arc welding. So in all cases, we're talking about 60 millimeter strip. 0.5 is the most common thickness that's used. So 60 millimeter strip. We're trying to achieve this 347 overlay. It's a very common grade of overlay for corrosion resistance in various industries. So it's a very common one. If we're talking submerged arc welding, then the travel speed that you can achieve is 10 centimeters per minute, and that will take you 750 amps. However, because of the dilution with this process, then you actually need two layers. So you need a buffer layer, a buttering layer, whichever way you want to describe it. So you need a first layer on there of 309L. So you're going to result in a bead height of, you see everything else as a single layer and it's 4.5 millimeters high. With a submerged arc, you're talking 2 times 4.5 millimeters. So is that possible? Is that allowed in the client specification? Are you allowed an overlay that thick? But obviously it's going to take time. We're talking 14 kilograms an hour, but that's just for a single layer, so that you need 2 of those. So you know that's halved in effect, or the production time is doubled. Okay, the entry level, if you like, electroslag welding, to achieve the same chemistry. We're talking a different type of strip, 2111 LMB, but this can travel at 18 centimeters a minute and deposit 22 kilograms an hour. And the jump there on the power supply required is from 750 to 1250. We'll jump over to high speed. So this is the best case. This is what we're talking about. Best case scenario, should you wish to achieve the maximum productivity that you can. With electroslag welding and a high speed flux, electroslag welding with a high speed flux, we're talking a travel speed of 400 millimeters a minute. That's huge. Okay, with a deposition rate of 51 kilograms. If you remember right at the start, we're talking 14, but that's in effect halved, so that's 7 up to 51. It's absolutely huge. Okay, you can achieve it in a single layer, but you need 2100 amps. So it's a big power supply. Okay, but we're talking about maximizing what's available. We do have a medium speed, if you like, somewhere in the middle. So we're overalloying the strip, and the strip and flux combination enables you to achieve 32 kilograms a minute. So it's somewhere in between the entry level and the high speed. Somewhere in between, we've got a combination that will work, that will take 1600 amps. So a machine below 2000, above 2000 is a big difference. Okay. In terms of total welding hours, so we're talking a 4 meter diameter, 20 meters long vessel. So it could be anything, and this is not untypical at all. 4 meter diameter, 20 meters long, and we need this 347 overlay. We're going to use 60 millimeter wide strip, and the total welding hours here, we're talking for submerged arc welding. This is just for a single layer, so we're nearly up at 600 hours for a single layer. So obviously you need 2 layers on there, so that's double. So that's 1150 hours. Okay, with entry level electroslag welding, you're talking 450 hours. Okay, so this is a single layer, that's it, that's your welding time, 450 hours in total. So that's a huge saving. You go to the medium speed electroslag welding, then it comes below 200. And for the high speed, you're talking 120, 125 hours, I think. So it's a huge difference. This is welding time. This is overlay welding time. Okay, so instead of talking weeks and weeks of welding, you could have this done basically in under 2 weeks. That's the difference. Okay. 2 things I want to mention. Again, the size of the power sources required. As you get faster, the number of hours reduce, but the number of amps increases. I've got to say that again. And again, the bead height with a single layer, we're talking 4.5 millimeters. So on the submerged arc, you need 2. Okay, so that's a massive increase in weight, apart from anything else, and cost of the strip, and cost of the flux, and cost of the welding time. So what grades are available? I would say, as with all of certainly the Exaton products, we talk about microelements, and I know I've mentioned these before in other presentations, but it's worth knowing. So these are microelements that are added to the melt. They don't appear in any of the specifications, and they would not appear on a certificate of conformance because they're so small. So these are the little additions of various elements that have been developed by the manufacturer in order to give these benefits. So these are very tiny additions, but they do have a very big effect. And the development in these grades has really been all about this. Anybody can make a 316L, but not everybody can make a 316L that can deposit high speed, good quality, give good chemistry, blah, blah, blah. So the benefits that these microelements give are things like improve the surface, improve the level, the quality of the surface deposit, fluidity of the weld pool, it's all, can be affected by these things. Increase the deposition rate. This is what we're talking about. We're trying to maximise productivity. So these elements, these help to do this. And as well, corrosion resistance. So I'll stress again, they wouldn't appear on the certificate because they're so small, and it doesn't affect the ISO specification. It still conforms to the same grade. So in terms of the grades that are available, austenitic stainless steels, 316L, 347, etc. There's a quite a big range, and they're available in normal, medium, high-speed overlays. So it's what your budget is, basically, what you're trying to achieve. You know, how big is the amount of overlay that you're trying to do. Going between 10 kilograms an hour to 50 kilograms an hour is not a big problem if you've only got 100 kilograms to deposit. But if you've got 100 tons, then obviously it's worth thinking about. We also have super austenitics like 385, 310 LMO. So again, dependent upon the chemistry of what you're trying to achieve in your overlay, we have options. Duplexers and super duplex, these are available. Would like to note that the Exaton duplex grade 2283L is unique in that it's got a balanced chemistry, whereas everybody else has to do a post-weld heat treatment. On this one, you don't. Okay, it's worth noticing. We do have nickel alloys, nickel chrome moly 3, chrome moly 4, nickel iron chrome 1. And again, we've got, there are an extensive range of fluxes that go with it. Obviously, we've developed these to enable correct composition, correct welding parameters, slag removal, increase the deposition rate, have a good weld bead. All of these things are affected by the flux. We've got high-speed grades for stainless steels, the Exaton 49S and ESAB 1014. And then we've also got high speed for nickel alloys as well. Okay, so the range, the portfolio is quite large. This is a summary just put together various options. You can see there are a number of options to achieve the same amount of chemistry. So there's a number. There's not a single solution, depending upon the equipment that you've got, the amount you want to spend. Okay, and so there are a number of options. All I'm trying to illustrate is that, say, for 347, you're trying to end up with an 18 chrome 8 nickel and niobium overlay. So we've got 1, 2, 3, 4, 5 options, 2 with submerged arc and 3 with electroslag welding. Okay, so there are options. It's not a single answer. There's not a single option that you have to go down. Okay. ESAB do a very handy strip cladding handbook that's got lots of a lot of the notes of sort of things that I've talked about in terms of details of the processes, but also obviously it's got the grades and the fluxes. There are some parameters suggested in there as well. It's a useful book. Again, please let me know if I can send you one. Typical applications, exactly what you'd expect. All kinds of vessels. We've seen this photograph before, but that's fairly typical. I would like to stress that it's not just for the inside of round vessels or flat plates. If you can manipulate the component to be welded into a horizontal position, then you can strip weld it. So you can see this is obviously the center of an enormous ball valve, and it's been strip welded on the outside. Everything that you see in there is probably clad with strip. Reactor vessels that you see, all of these have been overlaid in using these processes. The heat exchanger, okay, these are the heater tubes, the tube sheets, I should say. The tube sheets, that's been put on a turntable, and you can see the overlay going on top. You can see the slag coming off as it's cooling down. So thank you very much. That's me finished. I hope it was a useful insight. Please don't hesitate to get in touch with any of us. Our phone and emails are there. And the only thing I would like to mention is that the next presentation I'll be doing is specifically on covered electrodes and MMA welding. This is one that's been requested by a number of people. Basically, what's changed, what's happened. MMA welding's been around 100 years. You know, what's new now, what's available now. what are the advances, what's the research that's going into it. So thank you very much, and back to you, Clemente.
Thank you, Peter. Well received. As well, thank you all of you for your participation and the good questions highlighted. And I start with the first question which came in, and that's, should the flux be dried before use? And what is the recommended ratio of new to recycle flux? So the question is dry of the flux before use it, and how much is the recycling of the flux?
I can take this one if you
like. Please.
Thank you. Usually the recommendation is to use at least one part of a new flux out of 3 parts of the recycled. So 1/3 more or less. And then about redrying, usually it's not mandatory, because if the flux and the box, the bucket are still unopened and new, so it means that the flux has received the customer warehouse in the proper condition as produced. So usually it's not mandatory, but for tough applications, in many cases is still recommended, because it will improve the weld, the slag release, the bit shape, and so on. So maybe I understand it might take some time to redry it, and it's a bit of expensive exercise, of course, but it might lead to savings some man hours later on during the production, because of not repairs, but maybe some less cleaning activities.
All right, thank you very much, Paolo. I have the next question, which has been typed in, and it's, does this electroslug welding need a certain type of power sources? We have an ESAB LAE 1250 available. Can we weld with the electroslug process by using that welding power source?
Do you want me to say that, Clemente?
Yeah.
Yeah, absolutely. You've got a power source that can deliver 1250 amps. So providing you select the parameters that will fit, then absolutely fine. There's no special power sources for electroslag or submerged arc. It's a power source. And the difference is really in the use of the flux, the different types of flux. So yeah, so select a process whereby 1250 amps is enough. Does that make sense, Clemente?
It makes sense. It makes sense. 1200 amperes. It's enough. 1200 amperes. Important is that we have a duty cycle of 100% in that case, and but for sure, if it is not a 60mm strip, a 30 millimeters can be welded.
Yes, that's exactly what I was going to say. I'll put this slide back on the screen, and we're talking here for 60 millimeters wide strip, requiring 1250 amps. Well, if we went to 30 millimeter wide strip, then the requirement would be halved. Obviously, the deposition rate would be halved, but you'd still be faster than using submerged arc at the same width.
Exactly.
Yeah.
All right. Then the next question is, would you recommend magnetic steering for strip overlay welding?
I can take this one.
Please.
Usually magnetic steering device is needed at high current, and that also means, of course, high speed when 90 millimeter strips are used. Usually it's not necessary to have the magnetic steering device when 30 and 60 are used.
All right. I come to the next one. If we like to test the strip or the flux, can you be as of support at site?
Yes, nothing would give me more pleasure, to be honest. We've been stuck behind our laptops for too long. I'm more than happy.
Yes.
We do employ a lot of people. We've got a lot of technical guys, a lot of engineers all around Europe. And absolutely, if if there's a requirement for us to be somewhere, we'll be there to support.
All right. Good. Thank you very much, Peter. And then I have a question which came in German, and as I speak German as well, the question is, wie verhält sich mit den Schweißkosten von Submerged Arc Welding, also UP-Schweiß, gegenüber Electroslug Welding? So if I translate it right in English is, what is the ratio, the difference of the welding cost compared in Electroslug compared to Submerged Arc Welding? So maybe, Peter, you can show us the slides that we had where you compared the electroslug welding compared to the this one, or also the next one, you know, when we see the hours exactly. So here we see the submerged arc welding required 2 layers, and it is 600 it is somewhere at 600 hours that you need to use to clad a vessel which is 4 meters in diameter and 20 meters long.
No, it's twice that. That's just for the one layer, Clementi. Sorry.
Yes, and you need to do it twice. Exactly, yeah. You need to do it twice. Huh?
Yeah.
If you do it in electroslug and you do it in normal speed, you do only 1 layer, and you are above, or let's say, around 450 hours. So if you then count the cost, the manning hours that you are using, then you have a significant, how to say, recover or gain that you have. At the same time, you have also welding time that you regain, which you can use for a new production on that regards.
Yeah,
okay.
That's clear. Yeah, that's clear.
Okay, would you like to add something, Peter or Paolo?
No, I think you took it right.
Yeah, no, that's fine.
Unless you translate it in German, and my German is less than 0. Was it the question maybe about the welding consumables as such, or about
no, the total cost? The total cost.
Ah, okay.
As I interpreted it.
Okay.
And then electroslug should be, the question is electroslug the 721 process?
Oh, that I don't recall. This I need to check.
No, I'm sorry, I can't.
No,
I can't remember.
Okay,
let's see. Maybe if we have more questions, maybe we can take that ones. Meanwhile, that I check, but I'm not sure I have a quick answer there.
No, but that's okay, Paolo. If you like to send a mail, so we can respond you on that regards.
So I'm just
okay.
desperately trying to check it up.
I have it somewhere, but where did I place it?
Electroslug welding is type 72. Yes.
Ah, okay. Thank
you. Whether that's for the first types of electroslug welding, if you like, you know, the type that people use for welding train tracks together. Type 72 is definitely electroslug welding, but I'm not sure that it counts. That it would count for electroslag strip weld overlay. I can't see that. Please send an email and we'll research it. Never been asked it before. Thank you. Good question.
Yeah. And then the next question that I have, it's probably related to the question regarding the welding cost. It says manpower is reduced during electroslug welding. That's clear. But what's about the cost per meter welding?
Again, that's the cost of the consumables, isn't it? That's the cost of the strip and flux. That's what they're talking about, isn't it? And well, there's 2 answers really. Yeah, if you're using an over alloy, if the strip is over alloyed, then it costs more money. We're not trying to hide behind this at all. There are more elements in it. The difference between 2111 and 2311 is that there's 2% more chrome in that one, for example. So in order to compensate for you to go quicker, then yes, you need to over alloy, and the over alloys will cost more. So yeah, it's an equation, it's a balance. There's there's no single answer. Like we said, there's a number of options for everything really. I've only listed 3 different grades down there: 304, 347, and 316. But just about for most grades that people want to overlay, there are a number of options. And yeah, it's a calculation. It's a calculation that's quite easy to work out.
All right, thank you very much, Peter. Then we have another question which came in. Is can be achieved the 7mm high on one layer run?
That was for you, Paolo.
Yes, thank you. It is technically possible, but there is a high risk on having slag inclusion on the overlaps, because usually it's the preferred thickness is around 5mm per layer or per run. When it's getting to 7, it's possible, but you need to pay much attention on the overlaps.
I've had instances on the opposite way where the specification's been a maximum height of, I think it was 3mm, and again that's just as difficult. So obviously you've got dilution in there, and to achieve the chemistry on such a thin overlay, it makes a big difference, and it's tricky. It can be done, but it's tricky. But I absolutely agree with you there, Paolo, about 7mm. Yeah, I think that's pushing it. Can be done, but yeah, with care.
Right.
And maybe that is one good example where the magnetic steering device might help.
Yes, absolutely. Yeah, to change the shape of the bead to make sure it it overlays,
more
overlaps.
The sides of the beads more rounded, so that you reduce the risk. Yeah,
good question.
I have another one which is very interesting. Why Exoton 2283L strip, means the duplex one, don't need heat treatment while others needs?
Paolo, I'll let you answer that.
You have the complete background probably, because this one, no, I mean, because of this, I mean, of course, the weld deposit is richer in nickel, so you are having a better, how do you say it in English?
It's the balance which
balance phased, yes, exactly, in the deposition, and also because you are not using. We are suggesting and promoting neutral fluxes, so that you also have more homogeneous chemistry in the weld deposit rather than using alloying fluxes.
Exactly, because we are having more than 2% more nickel in the strip, means that we are getting on a good balance of ferrite austenite after the welding process or after the cladding process, and that's why we don't need to do a reconditioning of the weld metal.
There's an added problem with the duplex, isn't there? That you're not just trying to achieve a chemistry, you've also got to get the correct phase balance. So it's an added issue, and the way that everybody else does it, they have to do a post-weld heat treatment to get the balance of ferrite and austenite back. Whereas, because, as Clemente said, of the over alloy and the design of the chemistry in 2283L means you don't have to. Again, good question.
And yeah, it is really good, good session that we have here. All right, but this was the last question that I see in the box. From that point of view, thank you very much. Please note down Peter's and my contact details, as well Paulo's. I think it's also Paulo's contact details there, exactly, from the screen. Yes. We are already now very happy to answer further questions which will come up. Please don't hesitate to ask also for the presentation. We want to send it out. And with that said, we wish you all a successful rest of the day, and see you soon in the next live event in 1 month. Thank you very much, and bye-bye.
Thank you.
Thank you all. Bye.